Hi, welcome to BC Video 10.5a, Part 1, Intro to Polar Area.
So in 10.5, we're going to do polar area and polar arc length. So just as a review, if you remember when we did rectangular area, we took our space, we started off with the easy case, a region bounded by a curve, the x-axis, and two vertical lines. And what we did is we looked at it as a bunch of skinny little rectangles. So the area of a rectangle was the width of the rectangle, which we decided to make all these widths the same, dx, and the heights of the various rectangles, which are the various f of x's. And then we're going to add them all up, which is where the s comes from, the sum, from the beginning to the end, which is from x equals a to x equals b, which were vertical line borders. So it was bordered on the left by x equals a, on the top by x equals b. Sorry, on the left by x equals a, on the right by x equals b, on the top by your f of x, and on the bottom by the x-axis. Well, now we're going to be dealing with polar area. So we're not going to break it up into rectangles. What we're going to do is break it up into sectors. So little teeny tiny slivers, slices of pie. So we're going to take an example here where we have a polar curve, r equals f of theta, the black curve, and let's say it's bordered by these two lines through the poles, as opposed to over here it was bordered by two vertical lines. Now it's bordered by two lines through the curve, through the pole. So we're going to look at the formula for the area of a sector. Now hopefully you remember the formula for the area of a sector. It is 1/2 r squared theta. So I'm showing you this down here. Area of a sector, if I gave you a right triangle in the middle and I told you the area of the circle was 20 inches squared, you would easily tell me the area of that sector is 5, because your brain would automatically look at this and go, oh, that's a quarter of the circle. Well, the reason it's a quarter of the circle is because 90 degrees is a quarter of 360 degrees. But instead of looking at it in degrees, if we look at radians, we would say the ratio of the central angle in radians, and instead of 360 degrees, 2 pi radians, would equal the same ratio as the area of the sector as to the area of the entire circle, which is pi r squared. If you do a cross product and cancel out the pi's and isolate the area, you get this famous formula, 1/2 r squared theta. So what we're going to do is we're going to take these tiny little slivers of sectors, all of whose areas are 1/2 r squared theta. So we're going to have little teeny tiny, instead of skinny little dx's, we have little teeny tiny d thetas, these little tiny angles. And then the integral is going to have to match this variable, which is going to be from theta equals alpha to theta equals beta, which are, in this case, are these two lines through the pole. So there is our formula for the polar area of a curve r equals f of theta, bounded by the curve and two lines through the pole, theta equals alpha and theta equals beta. And don't forget the 1/2, because that is a very common thing to forget. So here's our formula yet again. Make sure it's from theta equals to theta equals, don't forget the half. Find the area of the region. So this is numbers 5 through 16. This is like number 8, it's not quite number 8. Find the area of one petal of this rose. So going back to the roses, since this is 2 theta, we're going to have twice as much as 2, which is 4 petals. The petal length is 6. You can check if you plug in theta equals 0, you will get r equals 0. So there's your pole, which is the center of your circle. Because the angle is 2 theta, instead of plugging in pi over 2, I'll plug in half of that. 2 times pi over 4 is pi over 2. The sine of pi over 2 is 1, and I get r equals 6. So that gives me 6 comma pi over 4. So that gives me my first petal. There are 4 petals, and if I find the tangents, which I need this time, not just to graph it, but I need these tangents to the curve through the pole. So we find the tangents to the rose at the pole. We take our equation, replace r by 0, and solve. And we find out that theta equals 0, pi plus or minus pi over 2, pi, etc. So if I draw these tangents to the curve at the pole, you will see that the region I'm looking for is bordered by my r equals 6 sine 2 theta And my limits of integration are going to be from theta equals 0 to theta equals pi over 2, which are the tangents to the curve at the pole. So there's your 1/2 r squared d theta. Theta equals alpha to theta equals beta. So we established that that's from theta equals 0 to theta equals pi over 2. Our r was 6 sine 2 theta, so I have to square that. That'll give me 36 sine squared 2 theta, and then of course you have to remember that that's why we learned this. The sine of a double angle, sine squared of an angle is 1 minus the cosine of twice that angle all over 2. Okay? You'll pull the 1/2 out, etc., etc. You will pull the 36 out, and you should be able to integrate that. I do need for you to notice that there is no sharp turn here because it actually very smoothly will go down. If I go back to the actual curve itself, this will very smoothly come around here and smoothly come around there and smoothly come around here. So you'll be fine. Therefore, you could, if you wanted to, do from, for example, I did 0 to pi over 2. Oh, I'm sorry. This is just me actually working this out. So here's the sine squared formula, which is 1 minus the cosine of double that angle over 2. Pull out the half. Let u equal 1 minus, well, actually integrate 1 to get theta. Let u equal 4 theta. Derivative is 4. Introduce the 4, counteract with a quarter. Integral of cosine is sine. Plug in the pi over 2. Plug in the 0. Subtract, etc. And you'll get an area of 9 pi over 2.